audible to all of you? Hello.
Hello, sir.
My voice is clear and loud also.
Yes, sir.
So, good afternoon to all of you.
Good afternoon, sir.
So today's session is just an open session for week 10. Yesterday's session was taken by Subhajit, and I hope he just cleared whatever the concepts are there in week 10, mostly or almost all. He said to me after I just watched the session. Also, almost it cleared the topics, cover the topics. So today's session is just like a like if you have doubt, you will ask some activity practice, or maybe you have conceptual also. We can discuss those also.
Sir, may I ask question?
Yeah, sure.
Sir, I have a few questions in the activity questions which I'm able to do, but I'm not clear about.
So,
Is question 1 in 10.2.
they're nice. Which activity? 10.1?
10.17 and 8, sir.
10.2.
10.2. We have 10.2. Okay. So yeah, it's one by one. We will take those questions and discuss those. 10.2. So in this question, asking we have two functions, f1 and f2. F1 has continuous gradient at origin. F2 doesn't have, or F2 has continuous and F1 doesn't have.
Sir, actually question 1 first. And two before 2. Question 1. Yeah.
Okay. So consider a function this, and the gradient of the function is given at 1 1.
10.2, sir. 10.
Oh,
Sir,
sorry.
10.2, not 10.1. 10.2. Sorry, sir. 10.2.
So the second question.
Yeah, this one. Yeah, this one I was not able to check. No, the first one. I was not able to check. How do you check continuity, whether the derivative, partial derivative function is continuous or not?
So, okay, partial derivative. So how you are doing, how you are doing this, or if you did something,
first I found the partial derivative for x and y with respect to x and y, and then even there I faced a little bit of problems in derivating these terms. Yeah, and then I was not sure that when we are finding out, because when we talk about continuous, we see whether the limit exists and if it is equal to the value of the function at that particular point. So I'm assuming here the point would be 0 0. Yes. So which function do we have to put the values in to find the value, in fxy or in the partial derivative functions?
Okay, so okay, let me take then maybe this function we have. So we have function fx is equal to x squared sine 1 by x. 1 by x plus y. Plus y when non-zero, x is non-zero, and 0 when x is zero. We have this function, a function of two variables. So talking about the partial derivative is continuous or not. So you have to find the partial, first find the partial derivative with respect to, let's say I am finding with respect to y. So what it would be, there is two process, either using the limit s tending to 0 f of xy minus f of at 0 is asking upon h something, and I'm missing partial derivative with respect to x is y, sorry, y, so y plus h at 0 upon h, or just assuming to, like you are derivating, you are trying to get this partial derivative when you will write here right side is as x is non-zero, assuming to be this, and then do the partial derivative. So if you do this, what you will get, this term is going to be 0, there is no y, and this will give 1.
Will be 1.
Okay.
Yeah. This one was easy. It was the x one which was tough.
Okay. Okay. Yes. Okay. So now once you did this, you got this partial derivative is 1, assuming to be x non-zero. So what would be at 0? So it is the, here is the problem.
0.
So here is problem to what is going to be
1. Okay.
It is not necessary 1. That's the, now you have, so you have this step function, right? So because of this step function, you have to go with the definition, then it will be better to you. I don't know it is going to be 1, or because it's look like this is for x non-zero and you are substituting here as 0x. So for the case this is for non-zero x, it is happening, it gives 1, but not for 0.
Okay.
So you have to go
Okay.
with the definition here. So in that case, you have to like here substitute here now, like now you are obtaining this partial derivative with respect to y at 0. So let's take for okay. So this is now going to be 0 here, and this is going to be h only, and this is the partial derivative at 0. Now 0h is, it will give you partial derivative with respect to y at 0. Minute, I'm missing something. Limit h tending to 0 f of 0 plus h times 1. This is the exact definition on h. Okay. So in that case, yeah, I just missed that. So when your x is 0, the function value is going to be 0, as here the function is defined.
Yes.
So here, as you have taken your x is 0 here, so just to substitute, it is going to be 0 minus, again as x is 0 here
0.
for this function, this is 0 upon h, this is limit here, so this is going to be 0. Now see that
0.
when you are obtaining, when you are evaluating this partial derivative at 0, you got 1, but when you are assuming to x non-zero, your partial derivative is 1. So that's the, like when you have such kind of function, you have to go with the definition as you have in the limit form. Otherwise, you will not get the exact partial derivative at that point. Like here, you can easily.
In step function, we should use the first method, the definition.
Where is the problem? Yeah, normal thing is like if you are doing with at 1 or where is no beside this, assuming to be here, where is the problem for this function? On x-axis, only. On this line, this function have problem. Otherwise, apart from this, the function we have nicely. There is no issue with this. But the problem is when x is 0. On this line, have this problem for this function. So whenever you are dealing around this line or at some, like you have 0, 5. So in such kind of point, you have to better to go with the definition. So once you like you got this partial derivative with respect to y at 0 is 0. Okay. Now So you have this function value at 0, 0. Now this value of the function at 0, 0, you have this one. You still remain to go with the like you have to find the function when x is non-zero. So you have already partial derivative with respect to y. Already you as you evaluated, this is 1. Okay. Now what is the process? You have to check limit. What is the definition? Limit value should equal to the function value.
Yes.
That means xy goes to 0, 0, fy, and this is your function. And this function is exactly limit xy goes to 0, 0. Your function is, apart from this, this assuming to be c, this tells you your x is non-zero. So your function will be exactly as this one. And this is going to be 1. So
And
limit,
how x is 0, na? We are looking at the limit as it's approaching 0, 0.
approaching to, what do you mean by this approaching to 0, 0?
Okay, but it is not actually 0, 0.
Yeah, you are approaching to your function here. X and y are not 0. You are just coming to closer and closer. So in that case, you already evaluated this function, right? This is the assuming to be non-zero. So this is the case as you are getting this function. It may be not exactly constant. It may be different also, some function. As we can see for the x case also, we will see that for the case x.
Yes.
1. So now we see that limit is 1, but function value at 0, 0 you evaluated using this definition is 0. So 1 not equal to 0.
Yes.
Your function is not going to be continuous.
Sir, I have a question here. So you have put like using the limit formula, right, sir? So f of 0h, how it is 0, sir? Won't it be h because x goes to 0 and y will be h? Will it not be h in the numerator, sir?
Here,
This
one.
Yeah.
So, okay, so here is how it is going to be. So the reason is this, your x coordinate is 0 here.
Yes.
So whenever your x coordinate is 0, how your function is defined? Given that when x is 0, your function will be exactly 0.
Okay, okay, got it.
So no matter what is the y coordinate, but when x is 0, then your function is 0.
Okay, okay, sir.
So anyone else have doubt on this? So you got my point. What I want to tell you, like how we will check the continuity when you have a step function. Suppose
Yes,
you are the case that you are the case like your function is like, suppose your function is polynomial, something ax square plus by square, something is polynomial. So if you do the partial derivative, your function will be look like, again you will get a polynomial. Easily you can deal with that, and in that case value at that point, and whenever you
So
are
like it will
evaluating,
come, for example, in this, for example, if you take the same example, it partial derivative with respect to x will be 2ax. So in that case, when we are checking continuity, we will find the value of the function at ax squared plus by squared or at 2ax.
okay, so like for this function we have so like f, our function is, okay, let's do that maybe. So that you have x square sine 1 by x plus y for non-zero x and 0. So fx, what would be then? So again use the limit as tending to 0, because the problem is, so we want to find the, again, as it is around the 0, 0. So go with the definition, proper limit definition. So as you have this, so this is going to be 0 plus h, 0 minus f of 0, 0 upon it. This is the definition. Now in that case, your function is now going to be h only here and 0. So as h is going to 0, it means your h is non-zero. So in that case, your function is defined like this. So value at that point when h is this one, h and 0, this function will behave like this. So it will go h square sine 1 by h. Okay. and now y is 0 here, so it will be 0 minus value at that point is 0 upon h, and this is the limit. So we'll cancel it out, so it will be h sine 1 by h limit h tending to 0. You have this function. Now what is going to be this limit? This is simple in one variable.
1.
This is going to be 1.
0, sir.
0, 1. How we are sharing this 0?
Because sine 1 by h divided by 1 by h, that is a become 1. Okay, no.
Oh yeah, you are, yeah, actually this is going to be like this. So,
But here is come infinity.
so
This
yeah,
is equal to 1.
as this is infinite by
Okay, infinity by infinity.
no, it is not going to be infinite by infinite.
It is 1, sir.
No,
1.
when you have this one, right, x tending to 0 sine this one,
X by x, sin x.
then it
Tends
is going
to
to be
1.
1.
Yes.
Can we not assume 1 by x to be some y or something?
Yes.
Before doing it?
But here is the sorry.
Can we not assume that 1 by x is equal to y and call it sine y by y?
Yeah.
But then limit tends to infinity. Sorry, limit tends to infinity.
Then
Tends
yeah,
to
that's the
That's
process.
the limit
That's
tends
the
to
process.
infinity.
What you will do, you will assuming to be y as y goes to infinity. Now your function will be we have like this. So
Yeah,
that's
yeah.
the process used to
Yeah.
be do. Now see that now this is changed. This is not exactly the same. So now how you will do this?
Mm-hmm.
So now in that case, what is going to be limited?
It
Will
can't be 1.
sin y maximum.
I think
It will
0.
be 0.
0.
It will be 0.
So I want
because
the
the
reason.
denominator
Because sin
is
y
tending
cannot
to
exceed 1.
Okay, yeah, that's the reason. Yes.
and y is
As
tending to infinity. The denominator is becoming very large.
very large. Yeah, that's all. That's all. So proper ways like yeah, you know that you know the idea how it's happening 0. So the reason is simple ways. If you somebody's asked, okay, show me the right in like in proper mathematical proof how it's going to be 0. So use your sandwich theorem. Sine function is lie between -1 to 1. So your function is exactly this one. See that now your function is okay. Let me resume. So your function is lying between in these two functions. And I want to find the limit as y goes to infinity. So this is going to be 0 and this function is also going to be 0. So sandwich theorem tells this should go to 0. This is the proper way to find the limit or writing way of finding the limit. So as here you find 0, so final thing is partial derivative with respect to x, partial derivative at 0 with respect to x you got 0. Now when somebody's asked, okay, now you want to find, you need to find when like you have to find the partial derivative when x is non-zero. Then you will compare, like then you will able to do limit xy goes to 0 this you will do, because exactly at that point you already got the value. When non-zero you have to find that function and then find the limit, and if this limit is exactly equal to this, then your function is going to be continuous. Partial derivative with respect to x, what is this? What you will get here? This is just y, assuming y as a constant, and you will do this using
Product.
product. So what is going to be? So okay, this is 2x sine 1 by x plus x square cos 1 by x and into it here into, now you have to as composition minus
Minus 1 by x square.
so this. So finally you have this function 2x sine 1 by x minus cos 1 by x. This is the function when x is non-zero case. And so like now your function is going to be like this, partial derivative with respect to x. So how your function is, it will be sine 1 by x minus cos 1 by x when x is non-zero, and you already got the value when x is 0. So for this function you have to check is going to be continuous at 0 0 or not. This is your function. So will limit exist for this function
Yes.
at 0 0?
Yes.
So how would we find for x is not equal to 0 because that's sine 1 by x?
It is given in the question.
So that means you have to find the limit of it. So how you will get limit xy goes to 0 0 f of x y, this is xy is exactly equal to this limit, just finding to the limit x tending to 0 of this function 2x sine 1 by x minus cos 1 by x, because there is no y. There is no y means there is no mean to writing like in this term, in this fashion. Only with respect to x side will be enough. So now in that case, what will be the limit here? Will limit will exist or not, or what will be the limit?
This is where I got stuck. I didn't know how to do this.
So this is now in a single variable. So in this case, like this is the two function f and g and added here, or subtracted here. So for this function you are able to get limit. What is going to be limit here? Same
That's
case
what
as
is
here, 0. But the problem with this function, so what is the, in that case you have to, whenever you will in such case you will say the limit of 2f minus g exists when f limit exists, g limit exists. The problem with this function g. So the problem with g, limit for g is exist or not? Cos is again we have like a
minus 1 to 1, right?
minus 1 to 1. Because as x goes to infinity larger and larger, we don't have exact value. Means what do you mean? This means this you will think as a in the this radian. In radian form you can think, and you will see that okay, larger and larger means your function is oscillating as goes to as x goes to infinity. So your degree, this angle is, you can think in radian. So for this g function limit is not exist. So then you will say limit as this limit is not exist. Fine.
Okay, because one part of it does not exist.
So yeah, that's the process. If you have two functions, this limit exists when separately these two limit exist, and just subtract those limit. If something
So
else.
in this, the limit of this function does not of fx also does not exist.
Not exist. So what is the answer then?
Both of them are not continuous.
So not continuous. So what is the answer for this question? Is 1 or 2 or 0 is given? Because both are not continuous, means not exist means now you are unable to, you have the function value but limit itself not exist.
In this question, like we had a step function. What I was asking earlier was that if we are checking continuity of say the partial derivative fx, then when we are finding out the value of the function to see whether the value of the limit is the same as the value of the function at that point, we will substitute or we'll find the value of the function fx or the whole function, that's fxy.
In whole function you will say no. So in that, now see, when you are checking, you finally you got the partial derivative, this one. With
So we
respect
put
to
the
x.
value in this. We have to put
Now
the
your
value in that.
function is this. So you have to check is this function is continuous is not. You finally found right here, as we at 0, 0 we got value, when x is non-zero we have this function. So this is your
So we
exactly
forget the other function for now.
now no need to go with this, like we are checking for this function now, partial derivative with respect to x,
Okay.
not for this function. Our
Okay.
exact
So
what we did.
continuity is with the new function that we've just found, the partial derivative function.
Yes, this one.
Can you repeat the last bit, please? Where you are explaining why we won't check for the other one.
So why we don't want to check. So the question is asked for the continuity of partial derivative with respect to x. So what we did, we actually we will find the partial derivative. Let me explain with an example. So what I want to say.
Yeah.
So suppose we have function f of xy is equal to ax square plus by square plus 2xy, or maybe let's say c. See here. So partial derivative with respect to x, what will it will be?
2ax
2by. No.
Sorry, with respect to
sorry. X with respect to x. So 2ax
plus cy.
plus cy. So this is your
C.
function. Now, so partial derivative with respect to x is continuous at 0, 0 or not. So this is the question. So now your function is changed now. Now this is your function. You have to check continuity for this function.
Right.
So what you will do, you will find the limit as xy goes to 0, 0 for this function. This is equal. This should equal to partial derivative at 0, 0. This should satisfy. You are not going to deal with this function. You are going to deal with this partial derivative, which we have already found here. Similarly, as here previous one we found. See that partial derivative exactly what is going to be when x is 0, non-zero, means on whole r you evaluated, you found, and now you have to check for this function.
One question. Let's say the partial derivative is continuous. Can I actually conclude that the function is continuous?
If partial derivative is continuous, so the condition is if this is going to be continuous, if this is continuous and this one also continuous, both partial derivative is continuous, then in that case your function is continuous.
Okay.
If both are continuous, then it is continuous. Then your function exactly continuous. Not only this continuous, at some particular point you are asking. If this is happening and partial derivative with respect to x and continuous, okay, so still one thing is remain. There is one theorem actually that is called there is one theorem, this partial derivative. The theorem is if both partial derivatives continuous in open ball around this point AP, in that case your function is going to be continuous, and not only continuous, it is going to be differentiable also at that one.
Okay.
Open ball means at this point, take something like for an open ball around AB means, if you want to ask an open ball around AB, so the definition will be for this is, so the collection of those points such that x minus a, or let's say x minus a here is a minus x, or maybe whatever y minus b whole square. Okay, this is going to be less than 1. So this is one kind of open ball around of radius less than 1 in R2, because here is AB. So you take a open ball around, you have collected those points who have distance less than 1. So in the ball around, your function is going to be continuous. Then you will say your function is, if the partial derivative is continuous, then your function is going to be continuous. Not only continuous, it will be differentiable. So what I told for this open ball, this definition is clear. Open ball means this one. So writing to be this one actually used to be write epsilon. Epsilon means any positive real number. And this is the definition of distance. Like I am collecting those points whose distance is less than epsilon. This is the mean of open ball.
Okay, but how is that different from the limit that we are actually talking about?
No. So this is checking for sufficient condition. Like your function is behaving like this in at point this and around this point. At point this, your function is behaving like this. So no need to find the limit of it. Just using the theorem. This is one theorem.
Okay.
Something name is that. Using this theorem, you will say function is going to be continuous. So here we're talking about the continuity of function, not partial derivative. Already we have assumption partial derivative is continuous. It took the attention. Maybe I mixed, so no need to tell this, because in this lecture this theorem is not talked. I think for gradient it is talked. I think there is in this video.
Gradient is nothing but partial derivative. Sum of, collection set of partial derivatives.
This one. This theorems. If the gradient is going to be continuous on some open ball around, see that open ball definition I have just given. This gradient means partial derivative need to be. This is the gradient means what? Partial derivative. So partial derivative exists and continuous open bar around at some point. Then for every unit vector, you are able to get directional derivative. So it is the one kind of sufficient condition. It is finding for the directional derivative. It is also tells you that your function is going to be continuous. Not only going to be continuous, your function is going to be differentiable also. It is more than this, not only directional derivative, it is telling more continuity of the function also, differentiability of the function also. Directional derivative is one portion of the differentiability, one separate part. So this is a very like this theorem, something not, there is no name. Maybe I have one book in that some name is of this theorem is. So that's all. So you can check that. And I also told you what do you mean by open ball. If you are not getting this theorem, this is the definition for open ball. Collection of those points whose distance is less than epsilon, or maybe if you want to fix, sir said an open ball. So you can think radius of open ball of radius. Or maybe as you open ball, open ball 2, 3, whatever you want, 0.001 something, whatever you want to radius of that ball, smaller, bigger. So yeah, anyone else have doubt?
Sir, could you look at also question 2 of the same exercise? Is it based on what you've just shown in this slide, the last line, all the tangents exist at a point?
Question 2. That's the thing here. That's the here.
That if the gradient exists.
So yeah, that's the telling here. See that your gradient is what? C comma K, as it is given. Partial derivative given means your gradient is given. And see that your function is constant here for all point of R2. It is actually
so the limit and so this will be continuous, both these derivatives.
Because this is a constant function, so it is going to be continuous for whole R2. In that case, what is going to be? Sufficient condition is also given. Directional derivative is one kind of partial derivative. Partial derivative is one kind of directional derivative, right? What I'm saying? Partial derivative. Partial derivative is one kind of directional derivative. What is the direction? Like I'm telling partial derivative with respect to x. So can you tell me the direction, in which direction I'm asking? If I'm saying to be this, so in which direction it tells you a directional derivative?
X-axis.
X-axis means 1, 0. So directional derivative in direction of 1, 0 is actually a partial derivative. So directional derivative in direction of 1 at a particular point means you are trying to get at a particular means you are finding the partial derivative of the function at that point. This is the mean. This side is directional derivative. See that in 1, 0 means partial derivative. At that point means partial derivative with respect to x at that point. Similarly for y is also. So this is telling something more, not only the like for existence of tangent line, what is the sufficient condition? In this already it is given.
If the gradient exists.
If gradient
and continuous.
is continuous.
Yes.
So
It was
yeah.
in that slide, it was at that point only where you had stopped.
Yes. Yeah, here is some same.
Last line. Yeah, this one.
Here is the conclusion is written. In the conclusion, telling same thing, all tangents at point A tilde exist when gradient is exist and continuous on some open ball around it. So for this question, see that what is happening, partial derivative with respect to x and y is given, that means gradient is given, and for all point the partial derivative is given. This means your gradient is not only and continuous, a constant function is one kind of continuous. So not only exist, it is continuous. So tangents is now going to exist. The last conclusion is important thing also for the tangent line.
So what about option 4? I didn't know.
This one. So do that, na. If you in this question, in this option asking for is your function is going to be this. So do the partial derivative if it is.
Okay. As simple as that.
Yes. Okay. So this is somebody have in 10 point he was talking about
10.1, sir, 7 and 8.
7 and 8.
Yes.
Okay. This one. So in this question, this we have function at point this, which are the direction that have directional derivative 0. So best way, what is the best way for doing? What is doubt here?
So I could not take differentiation this term. I mean, I got confused how to approach.
So directional derivative means, see, this function is very like, just do like in this question asking this lecture for the steepest ascent and descent means whatever the function is given, it is nice means it is nice means if you do the partial derivative. So partial derivative you need to evaluate using, no need to evaluate the definition, just doing, assuming to be like with respect to x you want to evaluate, assume y and z constant. Similarly for y, assume x and z constant.
I tried doing it, sir, but I got 4 as a solution.
4, this one.
Gradient as 4. No, 4 digit 4.
4 digit. No, you
I mean
have
4.
Why? What is the problem? Just need to be like thinking this one is as, just 1 minute. Just 1 minute. This one. I hope my screen is visible.
Yes, sir.
So you have this function f of xy is equal to e power 2x sine yz something. 2 into 2 e power 2x sine yz. So x, y, z, your function is in 3 variable. So with respect to x means assuming to be yz as a constant, then what would be? It would be, this is x here, 2x 2 sine yz, because only you will need to different. This is work as a constant. So this is going to be your,
Yes, sir.
with respect to y. With respect to with respect to x. With respect to y, again assume x as a constant and do with respect to y. Assume x and z constant. So again, this will work as a constant here. So this is going to be power 2x. Here is your main y variable. So this is going to be cos yz, but still it will work as a constant. So now into that here.
Y. Z, sir.
So, sorry, z it will be z. So z e power 2x cos yz.
Yes.
Similarly for z, it will be the same. Only here y will come and cos. It will be the same. Only y as work as a constant here. So this is your. Now what will be the gradient? Gradient is for general case only need to be substitute value here. 1 by 1 you can substitute and do for which directional derivative you are getting. I hope now able to do, right? In which direction you are going to be 0. Need to be take the dot product, which dot product gives you 0.
Okay.
Right?
Yeah. All right. Yeah.
Only you have this problem. How you are here? How you are doing? Like you have in this sections, right? Doubt like problem. Like
Yeah,
you
I got a bit
some
confused.
number 4.
Yeah.
What do you mean by 4? Right? Directional derivative you are getting 4.
Sir, actually function is 2e power 2x.
Yeah.
Oh, okay.
2e
So for
power
okay, 2
2x.
for first, now it is going to be 4 here. Now rest all will
4,
be
yes. So when I put the value x, y, z, then this 4 of the first fx function, partial derivative, it remains 4. Otherwise, everything else is 0. And then if you calculate, what do you say, orthogonal vector, then it doesn't match the given
with the
given
option.
options. Yes. So that's why.
Is that for everyone getting this? This is different.
Let's solve it, sir.
Huh?
Let's solve it.
No, only the remain part is only doing to this calculation.
Yes.
What is you have 0, pi by 2 and 1.
Pi by 2, 1.
So pi by 2 is, this gives you 4. This is 0 here,
Yeah.
4 into sine pi by 2 is 1. Okay. So this is for this is going to be 4. And for this,
Yes.
this is this pi by 2 will be 0 here. So 4, 0,
Yes.
0.
And 0, yes. So orthogonal vector for this does not match any of the options.
No, this one is working, right? this one, these two will give 0.
Sir, but a triple one also they have chosen answer.
So triple one is not going to be 0. This is going to be 0, not this one, this last one. So this is the
The
correct.
answer would be any with the 0 y z.
If you take dot product of it, you have 0, 4, 0, 0, dot product with 0, 1, 1. You have root 2 here. So what would be then? 0, 0, sorry, 0 plus 0 plus 0.
Anything
Okay,
with
yes.
this is 0, 1, 1.
Right, sir. Right.
Right, yes, yes.
And for the eighth question, you have to go with the each function. Which function give the directional derivative phi? Like it is given the direction at that point 1, 1 in the direction parallel to x-axis has magnitude phi. Which function is going to give this? You have to better to go with the function and choose that. Okay, so I'm leaving to you. This is better to go
Yes,
with
sir.
the option, like do the partial derivative and do find the like directional derivative and directional derivative at that point, and which one is going to be 5 will give 5. You can do that, you can match.
Okay, sir. Yeah.
Anyone else have doubt?
Hello, sir.
Yes,
Could you go question number 2, same activity?
same activity, question number 2. This one.
Not question number 3, sorry, sir.
This one.
Yes. So how to solve this?
Okay, and why this is just a partial derivative?
But that doesn't match. Partial
No,
derivative doesn't
again,
match.
if I will do, then as previous one, he was
How
saying
to-
like here is again not matching. I did the calculation. This is just
Okay,
a
could
partial
you
derivative.
show the option answer? I think answer would be last 2. Yes.
So maybe if
So
you
how
get the
to-
partial derivative, you are not able to get.
Yes.
What we meant to rapidly increasing in this direction at
How to
point,
solve? How to find it?
or maybe most rapidly decreasing most rapidly in the direction. This one at
How
point.
to find it? I can't find it.
Okay. So how are you doing? My question is from you. How are you doing? Ajay?
I only done partial derivative. Then I can't go further. So
What do you mean by most rapidly increasing?
most rapidly means most increasing. Where is it? Function are increasing, like
So
fx is used
again, my
to
question is, what do you mean by then steepest test? What is the use of this lecture then? What is the use of this lecture then?
Actually, lecture didn't understand properly.
In this lecture is easy. This lecture tells you in which direction your directional derivative is going to be in maximum, and in which direction your directional derivative is going to be minimum. So here, if you are not getting, here is exactly formula is also given. Like sir have did some example also. See that this formula is given. In which direction is steepest ascent, and in which direction is steepest descent.
Okay.
Direction is given. Only need to find del f at that point and divide by the norm. That's all.
Okay.
I think you
Okay.
didn't watch the lecture then.
So I watched but forget it. So I need to watch again.
This is just, that's why this is just an infer of that what is going to be most rapidly increasing, rapidly decreasing. Just wording is different. It's made
Okay.
rapidly steepest.
What is the means of ascent and descent?
Like as what do you like you know that ascent means was in Hindi it is चढ़ाई है something होता है कि मतलब पहाड़ पर
No.
चढ़ना, right? Your ascent means you are in the direction you are going to be is, and descent means you are going to down. Ascent means
Okay.
you are going to
Okay.
up, and descent means you are going to down.
Okay.
Which
Got it.
direction is going to be most steepest means it is not like this. In it is going to be like this. In which direction it is going to be very fast, most rapidly, and it's in which direction is going to be very this one.
Okay. Got it, sir. Thanks.
Okay, okay, Ajay. Anyone else have doubt?
Sir, 10.2 question 5.
10.2 question number 5. So yeah, that last one is very good. This one is very good question to be deal with. How if you don't know how to deal, this will I think explain to you in each question, a stepwise function in each question. You have to do with like this. If you have difficulty like if the function is step function, then you have to go with this. Otherwise, your function is not a stepwise function. Just do the partial derivative easily. You can do. Assuming to be with respect to x, assume rest variable constant and do find the function. If your
Sir,
function
this
is,
was very helpful. Otherwise, I would not have realized that in step function, this is how we're supposed to proceed.
so for every function, do like this. Well, no, means for every like this is the process for any function. This is the mean also. So you have this okay, this tangent line. So what you have doubt with here?
I mean, how do we check parallel to this line? Is it all about affine spaces and all that? I don't understand.
Parallel to this line. So okay, let me show you the in lecture itself. Maybe you will relate and you will itself give the answer. Here, this one. So here, this one. This is the parametric equation. Is everyone able to get what do you mean by parametric equation of a line? Why we needed this form? No, Vidya, you?
With the parametric, basically we're able to find each of these x, t, y, t, z, t.
Yes, parametric means your t is going to be parameter. If you change as your t, you will get different points.
Yes.
In 2D also, like in Subhajit class in last session, told you the how what do you mean by this? Why we needed this kind of why we are not like my question is I'm asking like the question is in R2 you are able to get a line of equation like this y is equal to mx plus c something with the relation this one.
Yes.
But why we needed this kind of actually this one is also represent a line. Why we needed this kind of the answer is like because whenever you are like in 3D, so how you will like this is the line, so how you will relate this line this like this will contain three variable like the x y z sorry two variable and rest will be depend on it like the relation I mean to say. Actually such kind of like see that you have a relation like this, but in R3 you don't have relation like this. The reason is actually this one tells you a plane equation of a plane, not for line. So for whenever you are like in R2 sorry R3 R4 in more dimension whenever you will go, so mostly you will deal with the parametric equation because you are unable to find the exact relation. You have to need a parameter. Why this parameter is needed? Like line is actually one kind of real like if you denote in R2 if you, this is line, so line means what? This is one kind of we have like a real line also. So you can parameterize with the, like, assuming to be this is the real line, and you can parameterize it. If you change the value of t, assume here is t, for each t you are able to get value. So suppose your x is equal to a plus tu, y is equal to b plus tu in R2, I am saying. So still you are, this is the parametric equation in R2 something. Similarly in R3, so this parameter is easily help you to deal with in any R2, R3, R1, any, not R1, R2, R3, any. So that's why we need a parametric equation when we have more dimension, like apart from this R2. So suppose this is a line here, so we are able to make a parameter t, and for each t, suppose here is your t, this is real line. So t is here, for that you will get x value, which for the line it is given as a plus tu1. This is for tangent line is given b plus tu2, and z is equal to some value at that point, and fill some formula is written. But what I mean to say, what I mean to make understand, like I mean to say to all of you why we needed this parametric equation. The reason is this: we are unable to find exactly relation in x, y, and z kind of. So that's the reason we need a parameter. And why we are able to do this parameter? Because of this line, real line. This line can be think as a real line. So think as this line is, we can make as a parameter on real line, and then we are mapping to each, for each t we are mapping, and we are able to exact x, y, and z. Got it? No? Or I made more confused to you?
Sir, I didn't understand it with
It's
relation
going
to the
and coming.
question.
If you can take it a bite-sized things, probably it's going to be helpful. Can you explain the line once, the parametric form when you're talking about? It's
Okay,
still
so
y equal to mx plus c kind of a variant, right? Y is equal to mx plus c is also a parametric form.
So what I meant to say, why we needed this parameter, why we are not dealing with this one, why we are unable to get a relation x, y, and z. The problem is whenever you are in higher dimension, if you got a relation like this, it will tells you a plane. So that's why we needed a parametric equation of a line. One thing, and this in R2, suppose in R2 you have equation of a line like this. This line, this is a general line. This line can be changed also in parametric form, like this: x is equal to smt, y is equal to mt plus c.
Yeah.
This is one kind of parameter. Still, so this parameter tells you exactly the same line.
Yes.
So that's why the reason in the now you got my point why we need it, or any line in R2 also can be changed as a parametric equation.
That part is clear, but when you mentioned that the plane needs a line, why does the plane need a line? We are trying to only minimize the maximum.
Plane need a line? No. This will represent a plane, not a line. Plane need a line.
Yeah.
Sorry,
correct.
sorry. This represent a plane, not a line.
It's extruded along the z-axis. It's extruded along the z-axis. It's a plane. Yeah. That. Okay.
So actually, yeah, that's the mean why we needed this kind of parameter is, if you want to write like this, so actually this will represent a plane, not a line. So that's why when we are in higher dimension, we need a parametric equation to represent any line.
Okay, in that case, z is going to be at plus b into mt plus c.
No. So this is not a line. This is a plane. So no need to talk about this here. Just I am telling you, this is represent a plane, not a line. So whenever, like, I want to tell you, like here. Now let's back to the question. Here. So this you in this theory, sir is telling about a tangent line. So what is the equation of a tangent line? The question is here, like we have a function, this one. So the question is, what is the tangent line at point AB in direction of u1, u2? This is the question. So for line we are talking, this we have a function of two variable. So when you draw a tangent line of this function, where it will be lie? It will go in 3 dimensions. When you graph this function, we needed to graph 3 dimension, right? No.
Yeah.
To graphing this function, we needed 3 dimension. This variable is, this function in two variable is there, but to graphing this function we needed 3. This graph of this function is in R3. So whenever now the equation of the tangent in that R3, what would be? The parametric equation we needed. So tangent line at point AB in direction of this is, the formula is just written the parametric equation, which is P of U1 yt is equal to B of P of U2 and zt is equal to value at that point of the function plus t time directional derivative of the function in direction. Let's say this direction is u, in direction u at that point. This is the formula. Tangent line at point AB in direction of u1, u2. What do we mean by this? Suppose we have this function. So, and at this point we want in this direction tangent line. So this is your u1, u2. This is your point AB. This is the graph of the function, and this is the tangent line. The equation of tangent line is this one. So if for this question, let me back to here. This is the formula as here written. For this question, where is that? This one. Here xt is equal to given t, yt is given 1 plus 2t, and zt is given minus 3 by 5t. T here is, you can see that we have xt, yt is equal to 1 plus 2t, and z is equal to t minus z equal to minus 3 by 5 root 5 t. Can you compare here what is going to be something direction
Is
from
A
here?
0 and U1 1?
Yes.
That's all.
Yeah, that's the thing. That's the thing. Actually, from here you will get the direction, and direction is going to be 1, 2 for this function. Like here is 1 dot t, 2. This is the mean, right? From here you will infer that this tells you direction here, u1, u2 coordinates it will give. From here, as you can see that. So for this line, you got the direction. This is the direction. Change it to unit vector. This is going to be unit vector root 5. Once you got direction, change it to unit vector. Now your question is change here for this function. You have already, so find the tangent line at this point. Parallel to this means you already got the direction of this line. Means what do you mean by, suppose this is the direction of that line, so parallel means still your direction will be the same. That's why you are making it in
Sorry,
unit.
what I was confused was if U1 is 1 and U2 is 2, I mean, don't we have to divide by the norm? Where did that go? I mean,
yeah, you have to divide because you needed, like if two lines are parallel, right? If two lines are parallel, so if you want to find its direction, so how you will tell you? Like if you generally talk about this direction, like this direction of these two lines are same, but how you will sure that once you change in unit vector, this tells you the both have same, like this direction of this line and this parallel means both Lines have the same direction. So find the direction of this line and make it in unit vector. So it will be the same. It will work as the same direction.
No, sir, but then here, then what is U1? Is it 1 or is it?
So from if you compare it, what is going to be U1 then? 1 only, right? Or if you are thinking, if you are thinking 3 by 3, okay. Suppose you are thinking like this is going to be 3 by 3, right? Still it is like we have like this, right? This is 3 by 3. It will the same one. If you are thinking like this, if you have doubt like this.
No, my doubt is that the U1 is a unit vector. If we are taking U1 as 1 and U2 as 2, then they are not unit vectors.
No, U1 and U2 are not two separate vectors. They are constituents of a vector U.
Yeah, but then together they should form a unit vector whose norm should be 1. So I didn't get it here. So is it?
You are thinking these are the unit vectors, so 1, 2 will give the unit vector. That's the process. That's the your thinking.
Yeah, I'm a bit confused here.
No. So if you are, suppose if you are getting like this, so actually this tells you the direction. If this is not in unit, make it unit. That's all. If it is not in unit vector, make it unit vector with divided by this.
Okay. So then using this unit vector and the point 1 minus 1
Get the equation
and that function, then we find the equation.
Yes.
Okay. It's something similar to question 7 of the same exercise. That one Shubhashish sir discussed, or I mean gave some hint towards yesterday. So that I've understood. I think that is what it is similar to.
Yeah, actually,
so we have it in the direction 1, 2.
Yeah. The same. Sorry. Continue.
So in this one, question 5, we have it in the direction 1, 2. Now we have to find it in the direction of the unit vector, and it will be parallel to that. So is that what it means? Okay, I think I got it. I'll try.
So actually, see, this is in this lecture, that is one thing, like tells you the direction U1, U2. But yeah, this is given, this question is given to, like, if you have, like, suppose still if you have doubt, okay, like if you have doubt, like you are unable to get the direction. Now I will ask you a question, something maybe you will get. Suppose you have a line, okay, in R2, y is equal to mx plus c. Suppose this is like, so what is going to be the, suppose R2, this is in R2. So what is the direction of this line in terms of vector I am saying? How you will get this?
Angle
our axis T
with slope and axis.
Okay, I know in the lecture they mentioned something that the slope is U2 by U1, something like that.
Right.
So the direction will be x-axis and the slope, I mean angle between those.
Slope and direction. So how you will get that? So let me tell you, like suppose you have 2 points, like if you take a point on this line, okay, take another point on this line. If you match these 2 lines, so whenever you draw a line using these 2 points, right, it will give the same. This line will be only possible passing through these 2 points.
Yes.
What it means, what it tells you, that the only 2 points will be able to decide this line. So using these 2 points, can you get, if you, in the coordinate system you already studied in math 1. If you have 2 points, so what is the this slope of the line? What is going to be the slope of the line if you have 2 points?
Change in y upon change.
y2 minus y1
minus y1.
This one is going to be, let's say if this is a1 b1 and this is a2 b2, so b2 minus
b1
upon a2 minus a1. This is going to be your tangent, right? This is the formula for slope of the line, right? So see that if this is giving the slope of the line, similarly if you have this point, if you subtract it here, b2 minus b, sorry, if you subtract these two lines, b minus a, subtract these two, sorry, these 2 points, what is going to be this? A2 minus a1, b2 minus b1. So actually, now divide with this. So this is actually tells you what is this telling? This tells you direction of the line. And once you have direction, make it unit vector.
Right.
Now you have this. This is your going to be unit vector in that direction. So if you are difficulty with this one, you have line this one. Okay, xt is equal to t, yt is equal to 1 plus 2t, and zt is equal to minus 3 upon root 5 and t. Okay, so get the point of this line. As substitute t is equal to 1. Okay, so you are going to be x is equal to 1, y is equal to 3, and z is equal to some number whatever you will get. Similarly, for t is equal to 2, find that, and you will get x is equal to y is equal to something. So only needed for getting the direction, we have to only 2 directions. So using on x and y, z is on depend on it. Z is depend on it. So you know not to consider it. Only using this x and y, subtract it and get the direction. Like if you substitute here 2, you will get 2 here, and this is going to be 5. Now the direction of the in that direction, like we want to find the direction. Now kind of make it b minus a, kind of only x and y, z is on depend on it, right? Because depend on this point in this, like z is depend on okay, just 1 minute. Where is that formula? Z is according to, okay, I'm missing something. So z is your, like if these two, this, sorry, if you have this in R3, this is on R3, still for this one, okay, should, this is going to be 1, this is going to be, yeah, it is giving the direction. Actually, z is depend on it, but this time I'm unable to relate it. So see that only using these two, like when you substitute t is equal to n, you get x and y. Again, you substitute t is equal to 2, you got x and y. And this direction we needed in 2 coordinates, only x and y will decide that. So as you can see that this is going to be your direction. Now make it in norm, the same direction you got. This is the process to getting that. Yeah, this time this z is actually depend on it, but because this z is actually give using these 3 points, it will give you to this. If you point wise, if you write x is equal to, say, let me write it, t is equal to 1, x is going to be 1, y is going to be here 3, and z is going to be minus, okay, this one. And when you substitute t is equal to 2, your x is here 2, y is 5, and z is minus 15. 5. Okay, so this we have. Now this is one point in R3. So this, what do you mean substituting t equal to 1 means you are getting a point for this line. Okay, so this will give a point, this will give another point, another set of point, another point. Now b minus a, what it will give, okay, fine, this will work. So b minus will give 1, 2, and this is minus 12 by, or maybe not 12, minus 12 by root 5. This is the direction of the line. B minus will give direction of the line. Okay, but for our case only we needed 2 coordinate. Direction is for needed 2 coordinate, so you will not consider this one, you will consider only this one and make it unit. This is your going to be unit vector. Sorry, this is going to be unit vector, and then this will give you direction, right? The same thing as you studied in math 1, the same process is happening here. There is nothing else, there is no differences. Vidya, you got that? I don't know. Ravi, don't. Am I audible?
Yes,
Yeah.
sir.
So what I don't know what I want to tell you. Is it clear? No.
Partially, sir.
Partially. See, the same thing as in math when you did. Like if you have 2 points tell you the slope of the line, using this formula you used to deal with that. And also if you think with the line in R2 direction kind of thing. So still it will the same thing is it's telling, just divide with the norm, it will tell the direction. Direction is also one kind of slope. Direction is also tells you the slope. Like once you got this direction, this one in this form, in this form somebody is asked what is going to be the slope of this line, just divide the second coordinate with the first coordinate. This is the same thing as you can directly go to infer here also. Sorry, here is a1, a2 minus a1, as we have this one. This is going to be the slope here. Everything is going when you come to in R3 also, get a point, get another point, subtract it, you will get a, this will tell when you subtract it here, this will tells your direction. But this point is in R3, our work is on only for R2. So you can think they take these 2 points, it will tell you that in that direction they take these 2 points, divide with the norm, and it will give you the direction. Otherwise, this is if you have difficulty, this one compare with this one, the previous one, as you have compare this with the or whatever the metric equation, from there also you can take the direction. And if you make it in norm and then use that. Yes, no.
So maybe when we do ourselves, it will be more clear. Otherwise, the theoretical part is clear.
Actually, whatever the coefficient, like these coefficients, actually one kind of, this is called directional derivative. The coefficients are directional derivative in coordinate geometry. Directional coefficient, something is made in coordinate geometry. Proportional directional, something is name is there when you study in, but no matter. Here is only the using the lecture you can do that. The coefficients tells you the direction, and once you using the coefficient, get the direction, divide with the norm, you will get exactly the direction of this line. 2 lines are parallel means they have the same unit vector. 2 lines are parallel means, if you suppose this, you have 2 lines here, if you have able to get direction, make it unit. When once you change this in unit vector, it will tells you that you will get the same unit vector. That's the mean here. 2 lines are parallel means only two lines parallel means you have the same coefficient as you studied also, mt plus c. If these two lines are parallel means it will be the, this is going to be c1, this is going to be c. The coefficients are going to be the same, only this plus side is going to be different for the parallel line in R2 also. So same here is also, coefficients are going to be the same. As here you have xt, yt and zt something 1 plus 2t. So coefficient will tell you the slope of the line, as here you can compare. Only the plus things will tell you, okay, these two are different means it's telling you these two lines are parallel if they are c1 c2 not equal. Same thing is also happening here. There is no difference. The same are going to be the same, only c1 and c2 is going to be different for R2 as here also. Okay, anyone else have doubt?
Sir, could you look at 10.3 question 1?
No one have doubt. Deepika is asking 10.3, which question
Question
number?
1, yeah.
This one. If tangent plane exists at origin, right? Okay, so what is going to, for which function tangent plane is exists? This is just talking about the same thing. When you are sure that tangent plane is exist, the theorem tells you when it gives the surety that tangent plane is exist, it is going to be continuous and exist.
Gradient vector should be 0 at that point.
Gradient, not only 0, it should be exist. Not only 0, not 0, not, there is no mean to be 0. Asking for at origin means around some ball of origin. Suppose you have origin, so take a ball, means what the theorem tells you, your partial derivative should exist and continuous in around the open ball. So suppose you have function this one, root over 5 x square plus y square. Okay, we have this function. So what is partial derivative with respect to s? What is going to be? This is y into 1 by 2 into 2x x square plus y square. This is your partial derivative with respect to x. So this is 5x upon root over x square plus y square. The problem is here is it will create problem at 0 0. Similarly for y, it will give the same 5y upon root over x square plus y square. So your function is okay. Here is not a stepwise function. Here is fine. Okay, there is no issue. But the problem where you are taking the partial derivative with respect to x or y, it is like this. You are unable to get partial derivative at 0 0. So you have to go with the definition. Like if you substitute here f of x 0 0, it is undefined. So go with the definition. Once you go with the definition here, what is then 0 with respect to s, it is going to be f 0 minus.
Hello, sir. 0 0 is defined. 0 0 equals to 0.
No, it is 0 by 0 form.
Yes.
Denominator has 0.
So go with this definition.
Okay. When the denominator comes 0, then it will not give 0. Okay, got it.
So now go with the limit definition. So the partial derivative with respect to s at 0 0 is this one. Now at value at function at 0 is 0, and h0 is going to be 5 root over h square minus 0 upon h. This is going to be 5, and here is, see that, mod come upon h. Is this limit exist?
No, for positive we get plus 5, or negative we get negative minus 5.
Yeah, this limit is not exist, as
Yes.
h is going to be less than 0. Still it will give you a plus and minus. This is our finding the limit. This is 5 mod h, sorry, you can see that one by one you can deal. This you want to find the limit as x goes to 0. Assume y approaching to left side, from the left side. So this from the left side, what is going to be this? This is limit h tending to 0 from left side. This is 5h, it will work upon. This is upon h. This is upon h. Now this is negative, right? This is negative if you want to change it. This is upon h, but it is negative here. You are approaching to 0 from negative side. So this give -1. From positive side, if you approach here, so again, this is positive. Still, this tells you the positive thing, but below is going to be from positive. So it will give from positive side limit is 1. So limit is not exist at 0. So partial derivative as 0 is not exist for this function. And also you can see in the video itself, sir have told if you have such kind of function, partial derivative at 0 is not exist. Graphically you can see also, like in GeoGebra. Otherwise geometrically, algebraically you can see. I don't know, able to get.
So in this case, the tangent plane for this function will not exist.
Will not exist because your partial derivative is not exist at 0, but existence of sufficient condition for existence of tangent line is, or tangent plane is, right? In this question, tangent plane is its partial derivative should exist and continuous around some oval ball. Similarly, see now the second one is like a polynomial. This is a smooth. If you do everything easily, can be done here. For the third one, again 0 have some problem. You need to check and evaluate. Again, you have to find the partial derivative and do that. Okay, once you find if partial derivative is continuous or not at 0.
Okay.
Get it? No?
Yeah, actually I done it just intuitively and I felt that the second one was fine. So I gave the second answer, but I didn't know how to do this question.
So got the thing right?
Yes. Yes.
Anyone else have doubt?
Sir, can you take question number 5 from activity 10.3?
This one, right? Yes. This one, na? This 5. This are fine.
Hello, sir.
Hello. This one, right? This 10.3 question number 5. This one, na?
Yes, sir. Yes.
So, what is doubt here? This is actually good thing. One kind of affine is added here.
Yes, sir. I don't know. Probably I am not able to get the relation between vector space and the affine subspace. Probably.
Okay. So actually, okay.
It is
So
a parallel. Affine is parallel.
So,
Yeah, that I understand, but still.
Okay. What
According
is
to this question, I am not able to get.
F be a function from R2 to R. Okay. T be a tangent at a point. So T is a affine subspace of vector space R3 with respect to it. So okay, let me make a picture. Then it may be clear.
Yes, sir. Yes, sir.
So your function is from R2 to R, but your
Yes,
affine is talking about T is going to be a tangent and said that this tangent is affine in R3. So maybe how you are happening, how it's happening. So see tangent. Once you got the tangent, what do you mean by like graph of this function will lie in R3? This function is from R2 to R. When you graph this function, you needed extra dimension. This is
Yes,
x-axis, this is y-axis. When you substitute, you will get the value z. Like you have function this f. This function is we have like this f of x y is equal to some value. So when you graph this function, your graph will be in R3 because you substitute values and output you will get. And this that output you can think on a z axis like this. That's why your graph is going to be in R3. Okay. Now once you graph, so tangent plane is actually, what is the tangent plane? Tangent plane is collection of all those tangent lines. Sorry, mute. Please, everyone, mute yourself. So tangent at a point means you are getting a tangent plane in R3. Like suppose tangent point at AB for this function is, once you draw that, suppose here is, okay, here is somewhere AB. Okay. You got value here somewhere z is, when you substitute it here AB, it will give some value. Let's say this is C here. So once you draw the graph, it will be, let's suppose here is now the final thing. Once you graph this function, you substitute it here, you got value C here. So graph is here. Now tangent at this point means you are drawing this tangent in R3. Okay. So this is the mean. Now tangent plane, T is tangent plane. And remember in affine, what is affine? Affine say tangent is actually, this tangent is one kind of plane, right? Tangent means plane means tangent plane. This is one plane. And possible affine, revise that, possible affine subspaces in R3, what those are. Once you have R3, think as R3 as a vector space. So what are the possible affine subspaces in R3? Possible subspaces is R3 is what? Suppose you have this. This is, suppose this is your R3. Now this is vector space, I'm saying. This is your R3 vector space. Now affine means, what do you mean by affine? Affine means you have a subspace plus add a point in that. Yeah. Right? What is the definition of affine is? Add a point, add a point AB plus a subspace U, something you have U. So actually suppose, so what are the possible, now what are the possible subspaces? So
Points, lines, and planes.
Points, lines, which are passed through origin. So and affines are all possible planes, whatever the possible planes means. If you shift that, suppose you have 0 0, suppose you have line, this line, this is going to be a subspace. Now if you added a vector AB, add a vector, when you added a vector in this line, it will shift it to somewhere, will shift somewhere parallel, it will be parallelly. So this is one kind of affine. Similarly, possible subspace in plane, kind of a plane which pass through origin, right? A plane which will pass through origin will be a subspace. If you add a vector means it will shift somewhere. So this plane is shifted but parallelly. So plane is here, your tangent is this one. This is one plane. So that means it will be a shift of some plane. Surely it will be shift of some plane. That's why affine, this plane is actually, this tangent plane is an affine. So actually the reason is we see that in affine subspace video, the possible affine subspaces in R3 is points, lines, planes, all are affine subspace in R3. So this tangent plane is also a, this tangent plane is also a plane in R3. So that's why it is going to be an affine subspace in R3.
So when you have drawn R2 to R here, so since R is one dimension, it can only be a line, or we we can see this oval kind of thing. Will it come as oval or just a line or a curve?
It will give a real number. The R means it will give a real number.
Yeah.
But let's suppose this is okay. This is, suppose you are substituted value here x. So suppose this function is from R to R. So you are substituting values from x. You are substituting values from y, and you are getting values on R. So suppose this R is actually your z. Actually, you are getting a output in on this line. Zx is also a real line, right? X is also a real line. Y is also a real line. You are taking a, this is called intersection of these three lines. So you are substituting values from x from this line. This is, let's say this is R cross R to R. So you are, suppose this x-axis is a line. So you are taking values from this R and y values from this line, and you are getting output on this line, right? So when you draw, so it will be like you, when you graph of this function, it will be, you are able to draw in R3. But my point.
Okay. Trying to understand, sir. Okay, maybe I need to think, because
yeah, just think that the same thing is happening. This R is actually, think as the x-axis. X-axis is also a real line. Y-axis is also a real line. Similarly, Z-axis is also a real line. So you are substituting values from this real line and other values from this line y-axis and getting on a real line output. Assume those output you are getting on Z line. Z line is also a real line. You are getting values here. Suppose you are suppose your input is AB, so you will get output some Z. So if you graph like this, you will get like, suppose here your A, B, C. Similarly, collection of those points will give you the graph of that function. That's the meaning of graph. That's the meaning of, this is the mean. Like the same thing in R2. If your equation is y is equal to mx, your equation of line is equal to, what is happening here? Y mx. Same thing is happening. You are substituting values here and getting the output here, and you will tell, okay, this line is going to be like this. Same thing is, you are substituting values here. You are getting values on this line, but when you let's say this is A here, you got value B here somewhere. So this is A, this is B. So this is here. This is A, this is B. This is point on A line. Same thing is happening here also. So this is the graphing of the line. You are able to graph that line. The same thing, you are graphing this function.
So when we say the output is R, that's only talking about C, but we are plotting A comma B comma C. Okay.
Yes.
Okay.
So is it clear? Ayush?
Yes, sir. Yes, sir.
Actually, affine subspaces are the possible subspaces in R3 is 0 or R2 itself, and or lines passing through origin, plane passing through origin. And now affine subspaces just shift of that. So this tangent plane is shift of some, surely. Actually, suppose once you calculated tangent line of this function, let's say this is ax plus by. Suppose you calculated tangent line z is equal to some ax plus by. You calculated it. This is your tangent line for any function. Let's say this one. Okay.
Yes, sir.
So now what is going to be your affine corresponding affine subspace? Corresponding union subspace for this. This is going to be, you can think like this: ax plus by and plus z is equal to 0 something. Okay, just
manage z, sir.
Huh?
Ax plus by minus z equals to 0.
Ax plus by minus z is equal to 0.
So this is the equation for the affine space, right?
No. I just missed. Suppose your I just missing that. Suppose Z is equal to your equation, your tangent equation of the tangent plane is this one, ax plus by plus
By.
c. This
Yeah.
is your tangent plane. Suppose for this function you got tangent plane this. So
Yeah.
affine subspace is now your ax plus by minus z is equal to, sorry, this is, so this is the corresponding subspace for this affine subspace is this one. So if you draw this, let me draw it. This plane is, suppose tangent plane is this one. So corresponding this if you shift do this way, this is going to be your plane, and your tangent plane is shift of this. Your tangent plane, sorry, so tangent plane, this one is shift of this. This is actually, this plane is passed through origin.
So C will be constant over here, right?
Actually C is constant here. This is the making the shifting of that. And actually C is will help you if you see that C is value at that point, will value at that point something is, right? If you write the formula, Z is equal to value at that point plus f u x minus a plus f, sorry, fx fy a b y minus b. This is the formula for tangent plane. So here your c is value at that point plus fx minus, here minus is fx ab, here is multiplied with the multiply here. These are the constant, will included in the constant. This will work as a shifting of that. Otherwise, here this is going to be a tangent plane. So corresponding affine is corresponding subspace is this one. So this is one kind of making as a affining. This is affine. So our tangent plane are actually affine subspaces. Got my point?
Yes, sir.
If you rewatch again, then affine, and then maybe if you forget that, if you rewatch again and then do
Yeah,
that.
it will be more clear. Yes, sir.
Okay. Anyone else have doubt?
Sir, can you explain a little bit of linear approximation? I'm little confused in that. Actually, I'm not little, I'm completely confused in that.
Linear approximation is just a formula.
Yes,
Linear
sir. Can you explain a bit theoretically also?
Okay.
Formula.
This is the typical point.
Sir, it is related to tangent or what?
Actually, what is happening here?
Yeah.
What is happening here? Like your equation of the tangent is writing like this: value at that point plus fx ap x minus a plus fy ap y minus.
Y minus a minus
This is the formula for tangent for a function R2 to R.
That is a tangent plane.
This is our tangent plane.
Yeah.
And linear approximation, if you see that, this is the same, but it is writing like this, LF. And this is the same expression, I think, if you see that.
Yeah.
So what is,
it looks quite similar. That's why I am asking that what is the relation between those?
So the relation is a geometric approach. Like what is happening here, you are, see, tangents, if you see that degree of this is one kind of, like if you see that this is degree of variable x is 1, degree of variable is y is 1. Actually this tells you, this is saying that this is the mean of linear. Linear means what? Linear means your variable have degree 1. Whatever you have variable, that variable is going to be have degree 1. So linear means linear approximation. Linear approximation means if you have this function x, y, and z, if you have this function and graph of the function is this, suppose. So tangent, if you see that tangent, if you draw that, suppose this is this equation of this tangent in this one at this point. Okay, for this point AB, you have this one, let's say ABC. So you draw this function. Now what is happening here? This function will help you to find linear values around this point. Linearly values, like linear approximation, you are approximating your function. Approximating your function. Suppose you don't have your function, like you don't know, suppose somebody gave that like this. Suppose your function is this one from R2 to R, and said that your linear approximation for this function is a, let's say 2x plus 5y plus 2. So this is given for your function. Then linear approximation is, I ask that find the value, approximate value at this question is still remain to some portion is remain. Linear approximation at 1, 2. Okay. Linear approximation, let's say linear approximation of this function, this is given. So somebody is asked find the approximate value of the function at point 1.52. So what you will do? You just substitute value here. Just in place of x, just substitute 1.5, y is 2. So what is happening geometrically here? This approximation is actually tells you are approximating this function. You don't have exact function. In this question, you don't have exact function, but linear approximation tell you somewhat linearly, like some linear away values. It will tells you some just a small around. It will tell you the value. So in proper way, approximate this function with respect to this point. The function will be, the question will be approximate, find the approximate value of the function at this point with respect to this point. Means you are approximating your function at linear approximating, means you have already this one approximating your function, you are getting some values around this point. Means you are able to get.
Yeah.
That's the meaning. You are approximating your function, somewhat approximating linearly.
Linearly approximating the function.
And also, what is the use of actually what is happening in in simple function? You can suppose your function is from R to R. Your function is this one, R to R. So
Hello.
Hello, sir.
Oh.
Is it only for me or?
No, I'm also not able to hear.
Okay.
Yeah, same here.
I think there is some network issue from sir side.
Yes, I think.
Is there any textbook for this kind of, I mean, earlier it was linear algebra, but this is not a part of linear algebra, correct? The linear transformations and everything, it was linear algebra, you could see that. But
you can refer, I think you can refer B.S. Grewal.
B.S. Grewal, the title being?
Yeah, this is the title. No, this is the name of author, but you can find.
B.S. Grewal is an engineering mathematics textbook, but
yeah.
Is that the one that you're referring to, or is there another textbook?
Yeah. It is the same one.
Same book, okay. Thank you.
Very good text. Even if you solve the example, you will be it.
Okay.
hello everyone, am I audible? All of
Yes,
you?
Yes, you are now.
I got disconnected. Okay. So let me share my screen first. Yeah. In R2 actually, see the tangents are actually used to like at this point you are able to draw tangent, at this point able to draw tangent. Like this, if you able to draw, you don't have, if you don't have function, you somehow you are able to draw and approximate that function. So suppose you are, somebody has said that your tangents are like this. So that means you are able to draw somewhat rough diagram of that function. Linear approximation actually tells you that values at that point. So that means you are able to get those values at that point, and anyhow approximately you can draw the graph of function. Am I audible?
Yes,
Yes,
you
sir,
are.
yes.
Yes, you are.
So that's the mean of linear approximation.
I have
to
a
be
question.
Okay.
It is if we go for linear approximation, how accurate is our approximation going to be depends on the gradient, right? So is there a control on that one that we can say, okay, only to this extent it is possible, or it is going to diverge afterwards?
Yeah, actually, I don't have exposure. Like I don't have any much information. Yeah, actually, there is, and when you do numerical analysis, there is one Newton-Raphson theorem and others.
Yeah,
Those
yeah.
are actually will control you to how much error is applicable. Like there is one Newton-Raphson and numerical analysis. There are some theorems. Numerical analysis have Newton-Raphson bisection theorem. There are some theorems and another
Okay.
also. Those are actually makes control to you.
Okay. Okay.
So yeah, numerical analysis. That's one course in mathematics, numerical analysis.
Yeah.
Those things are, yeah, actually you are approximating, you are making error somehow. So in numerical analysis, there are some tools you can measure those errors.
Okay. Okay.
Sir, the practical assignment solution has not been uploaded for this week 10.
Yeah, I think so. Practice assignment.
It's not
Let me check
uploaded.
also. Let me check that.
Above, sir.
In which section it will be? Supplementary.
Supplementary content. Yes.
Oh, only it is week 9. Okay, okay. Okay. Today I will tell to upload.
Yeah, sir. Please. Thank you.
Anyone else have doubt?
Sir, I have a doubt in quiz 2. Can I ask that, sir?
Which two? Which two? From where I will get which two
Mock
questions?
question.
Mock question.
Okay, this one is mock.
Go to below.
This is
Down. Yes. This is. Solution is uploaded.
yeah, in India it will be.
Yes.
Oh, okay. So which question number?
That's similar matrices question, sir. I'm not sure if it is the same question number.
Okay, what? So you can tell what is the question there?
Yeah.
Just
You can tell the question. Maybe it will be more clear if you have.
just 1 minute, sir.
Yeah. Okay. Otherwise, anyone else have doubt?
Sir, can you check the solve with us question number 40?
Question number 4.
14, sir.
14. Okay, this one. Find the point on the plane closest to the origin. So how will you get that?
Firstly, I use the distance between XYZ from the origin by distance formula.
Yes. Yeah, the same thing. What is the idea? Suppose your points from the plane is X, Y, and Z, and the
Then
distance
I got
formula
confused.
from
I mean, I have to minimize the particular equation, right?
yes. Okay, you have to minimize it.
Yeah.
So minimum value of this function is so see that once you minimize, so like you have this function, okay.
And
So
then
see,
probably I'll have to
point,
substitute in
no,
that
no, so
particular.
no need to go with the minimize, like you have this one, right?
Okay.
You have this function. This is the distance formula from origin.
Yeah.
And these points are from plane.
Yeah.
So you have to, like, this question is given for only you have to take those points, like which point is satisfying that, and evaluate the value. So just substitute here your value, and which is going to be minimum. That's the meaning. Substitute here value,
Substitute the value. Okay.
and which is going to be minimum. That is the going to be, because here the points are given.
Yeah. Yeah.
So you have to take the minimum of that. Theoretically,
Whichever
if you
will
go
satisfy
actually,
the equation will be the answer.
actually the doing this whole thing is, there is one called Lagrange theorem. Lagrange theorem tells you the whole process, but we don't want to do that. Only from the points given, from the point you have to collect those. So here is just meaning
But
to
can
know
we do
which is
this
going
by
to be
process?
actually that process is you don't study it, like you have to know the week 11 part first. When you go with week 11 first, and then there is one extra thing, like finding the maxima minima of the function is from 11 week 11, you will get that. But here is one condition, that your point should satisfy this. So there is, for such kind of, to doing such kind of, that is called, there is Lagrange something, Lagrange maximum minimum. So there Lagrange theorem is there. Those theorem will help you exact. That is, this thing is not covered for this course. Lagrange theorem is not covered in this course.
Yeah, it is
Only
not in
covered
this
to
course.
know how is going to be max or minimum value. This question is asking for, are you understanding what do you mean by maximum value or minimum value? That's all. That could be infer from this substituting values in that function itself and conclude. That's my point.
Yeah, yeah. Yes, thanks.
Can I see the question?
Yes, yes.
I'll tell the matrices, sir. The first matrix, I'm telling row wise, 1 0 1 1. It's a 2 cross 2 matrix. Yeah. Second one is 1 1 0 1. And third one is 1 0 0 1.
1 0 and 0 1. So, and this asking for which is going to be similar.
Which pair is similar?
Yeah, which pair will be similar?
So now I can tell you one thing. This is one kind of activity question, not one kind of, exactly activity question of your similar matrix. In which week we have similar matrices? This one. And if you see the last question, this is the exactly same question. I think last question on this one. Asking for the which one is going
But
to be
in every option it is given, but they are not similar. But they are not similar.
They are not similar. They are not similar.
Yeah.
So this is the
And
same
even
question.
we have asked many times. We have told that if the basis will be not given, it is not easy to find whether it is similar or not.
Yes.
By all the properties, I satisfied that the B and C, sorry, A and C are similar, but that's why I did not take that option, because I have told that it is not easy to find whether it is similar or not. So I have selected that no one is similar.
Priya, you did this for this activity. So actually, this is given If you have practiced yourself, whatever your answer, if you infer that, so no need to solve much. Just pick that which is going to be similar.
No, sir, but all the options says they're not similar, right? So
Yeah.
for C, I got,
Yeah.
I mean, for 1001, the similar matrix should be the identity matrix. That I got, sir. But for
The property are satisfying, but again, they were saying in all the live session that it is not easy to find whether it is similar or not if it is not given the basis of it.
maybe I will tell how I tried in the exam, sir. What I did was
Yes. Yes.
I did like PA equal to BP because of the
Yes.
condition. Yeah, and I just chose P to be ABCD only. I was
Yes.
not able to sure of how to think about the matrix. So I did matrix multiplication of these two and try to equate. I was not able to get. So I thought none of them are similar. I tried for.
Yeah.
No, that's the approach. That's the approach. Here is that's the approach only. That's why I was going to tell
But
you.
sir,
But it's
in
okay.
ABCD, you will find the equation that will be this coordinate will be equals to this coordinate will be equals to this.
So
Yeah.
solve
So
those,
how
na?
will you say that this is equal? Firstly, you have to
Can
know
you-
that this satisfy this equation. How will we
When
know
you
that this
do for
satisfies?
A and B, sir, I'm not, for C I got it, sir, but for A and B, can you tell the answer says A and B are similar, but with the method I approached, whatever I told you, I'm not getting that. Can you just do A and B alone, sir?
Yeah, that's what A and B
Okay.
are
Okay.
the option.
So for B and C is not similar. You got?
For
Is it
C,
clear?
any similar matrix to C should be an identity matrix, no, sir?
No, not necessary. This is the same formula like saying to be the same. A equal to.
Sir,
let's
anyways,
say this
it
is.
doesn't satisfy the property as well as it is given the traces has to be similar. Same, sir.
Those are okay, but
Yeah.
the basic definition is this to satisfy. This is the definition.
Yeah, but the property is also there, na?
Property is one thing. If you have similar matrices, all property like rank will be same, determinant will be same,
Yeah.
test will be same.
Yeah.
But if these are
Sir,
same,
how
you
will we
can't.
find that P? Is it easy
So
to find
this
P?
is, yeah, this is the process. As we just now
Yes,
told
sir,
you.
P is there, but how, this is the P, but when we know that this satisfied the equation P is equals to BP, how will we know this satisfy the equation
If you
when
do
it
for
will be similar?
AB, I
You
think
put
that
And
will
how
help.
will
here
we firstly know
ABCD.
that
Hold
it will be
on.
similar? We can't assume that.
But just hold
Okay,
on.
okay,
Hold
okay.
on.
So
ABCD.
I will solve here. I will solve this.
Yeah, please.
So for BC, is it clear? How it is directly you can infer. What is tells you
Yeah.
that if you assuming identity, so it is going to be P inverse P itself. That means
Yeah.
identity.
Yeah.
So is your B is identity? No.
No.
Right?
Yeah.
That means B and C is not going to be similar.
Yeah.
Once you use the definition, you told that this is
Yeah.
not going to be. Similarly, you can check for C also.
Yeah.
Sorry, AC.
Yeah.
But remain to AB.
Yeah.
Now your A here is it is saying to be PA is equal to BP said BP like this, or maybe PA is equal to P inverse BP, which should happen.
Yeah.
This is the mean. So take P is A B C D, and this is your A is 1 0, this one, and BP is again the same thing. Take this one BP your 1 1 0 1, and P is A B C D. So what is going to be then a multiplication? Can you tell me? This is right. This is how much? What will be this? This is A, and this is A plus B. Sorry, A plus B, and this is B only. This is C plus D, and this is D only. Similarly here, what would be this A plus C? This is B plus B. This is C, and this is D. My multiplication is correct.
Yep.
Now these two says these two are equal. That is what? A plus B equal to A plus C. A can cancel here. Means you got B equal to C. One you have one condition. Now B plus D equal to B. That means you have D equal to 0. See, you are able to get some values here. 1 1 0 1 and 2 2 0 1 1 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 2 0 1 2 and C plus D equal to C here. Again, it tells you D equal to 0 and D equal to D last one is giving. That means you got D equal to 0 and B equal to C. Something you have, right? That means your
So
matrix
from
is
that
how it
we'll
will
have to
look like.
form P matrix and do the multiplication. So
That means now you see your A is unable to find A will independently will work. Okay. B and C are the same and D is 0.
is 0.
Now see, give some value to A and B. Like see what it is telling. Let's say A equal to 1 and B equal to 0 and 0 0. If you multiply that, what is happening? This is the same thing as you are getting. This is A is equal to 1 and rest all are I think 0. And here is if you give A value to 1 and rest are still, yeah. See that AP is going to be BP. Means your A is one kind of this. Sorry, P is your one kind of this.
I got it. So I think the mistake I did was like I multiplied these two and tried to equate directly. Like if we get same matrices, then I thought it was similar matrices. I think I didn't do the next step of determining P from this. That mistake I did.
But here is one problem. I made a mistake here. You cannot take B is equal to 0 because your P is not invertible. So take B is equal to -1 because you are failing to do all things. So you have to take P as invertible matrix. But still, if you do this multiplication, you will get the same thing. That means you are able to get some P, not exactly. There are many P exist. Right?
So if we get a P which is invertible, then we are okay. Is that the way?
Yes, then yeah.
But we are actually, when we are doing this A, B, C, D, I am actually doing, okay, it's only for P that I am doing, not P inverse. Okay. Okay.
Okay.
Yeah.
So if you got the idea. So if you have any doubt, or maybe it's now 4. So if you have doubt, you can ask, or we can close the session also. Up to you. Anyone have doubt?
There one general thing, the tutorial helps us a lot, but in week 11 there is no tutorial.
In
So
week 11 there is no tutorial. Okay. What is in week 11? No. Actually, this is just a theory part. There is no that's why there is no tutorial. The reason is sir have already solved so many examples first, and this is just a theory part. Like what is in that? Only just formula. If you are getting these all. So doing to be tutorial means just doing to be solving the question. That's why there is no tutorial. I think that's the reason. Only if you are satisfying this condition, that's all you can conclude. And already in that, sir have solved many questions. That's why there is no tutorial. Tutorial means if sir have did some less example, the main to be do tutorials will have to do more example to understand the topic.
So there will not much need of tutorial in that week.
There is not much need of tutorial. That's it. Yeah, yeah, okay. But if you are saying, then maybe we can create and maybe upload. But for the next time, maybe it will be available.
Then it will not be of my use.
No,
So
but I
don't do
think
it.
so it will not create a difficulty once you see this video, and if you only attend one live session, that's enough. Only the formulas are here, and in this only you need to remember some formulas. This condition, this conditions. There is only the condition. If you are satisfying this, substitute value, check if it is satisfying, just tell that okay, it is going to be maximum or minimum. The basic thing is in this, when is going, you are able to get a proper critical number of critical points, and which is in the week 10.
Week 10, yeah. Lecture number 4, I think. Yeah.
Okay.
So can you tell something about first principle?
First principle. Regard to? First
regarding
principle
the where to use. I mean, there used to be of two method, no? That where to use first principle and where to use another method.
for this multivariable.
Yes, sir.
First principle, second
Vasis
principle.
sir was using something like that, and then after my internet got disconnected.
Subhajit sir.
Yes, sir. First principle he used something.
Don't know. Okay. I don't know first principle. Just
Maybe I
we
will
were
watch
just,
the live session again.
actually first principle is, I think this one maybe just naming is there. Otherwise, first principle is regarding this maxima minima or critical point.
Derivative using first principle.
Oh, derivative.
Calculating derivative using the first principle.
This is the first or multivariable. Okay. So that I know the theorem, but regarding to the name, I don't know, because that is called first principle, that is called second principle. I
No
don't know.
worries, sir. I will watch the live session and maybe
Yeah,
then
just-
after I will see.
Yeah, maybe I
Because
will see that.
I also don't know that regarding which thing he was saying.
Okay, so yeah, okay, let's end the session now. If you have, you don't have doubt.
Okay, sir. Thank you so much.
Thank you
Thank
so
you.
much.
Thank you so much, sir. Thank you.
Thank you,
And
sir.
the result will be displayed today, right?
Results are out already.
Already out.
Alright.
Okay. Okay. Thanks. Bye, sir.
Sir, do please upload the practice assignment solution.
Yeah, sure. Yeah, I will just say note it.
Thank you, sir.
Sir, thank you, ma'am.
Thank you so much.
Thank
Bye.
you, sir.
Thank you. Bye.